very much. Thank you. Thank you for inviting me here back to I.A.P. And I love always coming to Paris and talking about this subject, which is one that I don't think we talk about enough as professional cosmologists. So part of my goal in the talk will be to convince you or persuade you or remind you that when we try to explain the origin of the universe, one of the things that we need to explain rather than assume from the start is the arrow of time, the difference between the past and the future. I say that the arrow of time is the single most obvious fact that we get from observational cosmology, the fact that the past is different from the future. We don't ordinarily connect it to cosmology. We want to try to convince you that connection is there. So first, let me remind you what the arrow of time is. It's, again, the fact that the past is different from the future. The fact that there are processes in nature which happen in one direction of time but not the other. Mechanical processes, mixing cream into coffee. Personal processes, aging over time. We're all born young, and we grow older, and then we die. It's always in that order. Benjamin Button was a fantasy, not a documentary. Society changes over time. The point is, if I show you any of these pictures, I don't need to label them as one in the past and one in the future. You know what the direction of time is in any one of these pictures. We have different access to the past and the future. We remember yesterday. None of us remembers tomorrow. I hope none of you remember what will happen tomorrow. We think that we have causality or free will toward the future. You can choose to stand up right now and leave the lecture, but you cannot choose to have never come to a lecture, since you are here now, right? You have different causal access to one direction of time than the other, and we'd like to understand why this is true. So in the past, if you were Aristotle trying to think about this, before modern physics came along, this was not even a question to be asked. This was just a fact about the universe that was blatantly obvious and sort of primitive. It doesn't need explanation. But now we are in a slightly different situation. Ever since Newtonian mechanics came along, we've been in a situation where every serious attempt at running down fundamental laws of physics, whether it's Newton or Maxwell's equations or general relativity or Schrödinger's equation or superstring theory, they all have the feature that they treat the past and future identically. That there's no difference between one direction of time or the other. And in particular, the laws of physics are reversible. So if you take two billiard balls or any simple system, a planet moving around a sun, a pendulum rocking back and forth, and you evolve it forward in time, you can take that movie and play it backwards. If you literally make a movie of billiard balls moving on a frictionless surface and play it backwards and show it to somebody, it looks fine. You would not be able to tell that it was being played backwards. It's only in the macroscopic world, where there are many, many moving parts, that we see this irreversibility to the universe. If you take warm water and put an ice cube in it and let it go, it will become a cool glass of water. If you get a cool glass of water and just let it sit there, it will remain a cool glass of water. So from this state, you don't know where you came. There's a million different movies that you could make of a diver going into a pool, spilling a cup of coffee. Make a movie of a macroscopic process and play it backwards in time, and it's instantly clear what direction it's going in. So the question is, how do you reconcile the fact that the fundamental laws of physics, as far as we know, are reversible, with the fact that the macroscopic world is not reversible? And I don't want to pretend this is a gigantic mystery. We have mostly solved this problem. It leaves us with a little bit of crucial solution that we don't yet have. So as scientists, it's a little loud, the microphone, but I tend to shout. As scientists, we try to make it quantitative. So we invent the second law of thermodynamics. This is the way of quantifying the fact that there's an arrow of time, which the past is different from the future. So it's this equation, the entropy in a closed system, as its derivative with respect to time, is greater than 0. The entropy of a closed system increases or remains constant. This equation is not invariant under time reversal. So as time goes on, you can start with a low entropy system, something that is organized, something that is orderly, like an unbroken egg. Thank you very much. And as time goes on, the egg could break, it could become more disorganized, the entropy goes up, the egg could become scrambled, the entropy goes up again. That's an easy movie to make. It always happens in this direction, never in the other direction. So what I want to claim is that the second law, the thermodynamic arrow of time that says that entropy increases, is underlying every manifestation of the difference between past and future. All of the different ways, memory and causality and aging and so forth, it's all because entropy is increasing. If you want to understand why there is this arrow of time or that arrow of time, you just need to understand the second law. And you might think that we do understand the second law. We have this guy, Ludwig Boltzmann, who in the 1870s helped explain what entropy is in terms of atoms, or molecules, or whatever, small pieces of small elementary constituents that make up the world. In the 1800s, physicists were slow to catch on to the idea of atoms. They were reluctant to believe in them. Chemists believed in atoms and molecules long before physicists did, because chemists knew they could explain the rates of different chemical reactions if you postulated atoms. But the physicists said, no, this idea of atoms should not be part of science, because you're postulating unobservable entities that we'll never be able to test, and science should be about testable things. Is a familiar kind of rhetorical move, even to this day. But Boltzmann and his friends, Maxwell, Gibbs, Thomson, said, the reason why you should believe atoms is because they help us explain things that we do observe, even if we don't observe them directly, like the second law. So I tell my students they should all aspire to what Boltzmann achieved, which is that he has an equation on his tombstone. You should always be asking, what is the equation that will be on your tombstone someday? The equation on Boltzmann's tombstone, which is not the one we call Boltzmann's equation, that's how good he was, is S equals K log W. This is Boltzmann's way of defining entropy for people who believe in atoms. So entropy was already around. The second law had already been formulated by the time Boltzmann came around, by Carnot and Clausius. But Boltzmann said, if you believe in atoms, then there's a feature of the world that says that entropy is not an independent property of stuff. It's a way of describing a certain amount of stuff. In particular, if you believe that the air in this room is made of atoms or molecules, there is a microscopic state that tells you the exact configuration of all the air molecules in the room. The position and the momentum of every single molecule. That's macro state. The micro state, the exact Newtonian configuration of stuff. But we don't observe that. When you look at the air, or when you measure it with instruments or anything like that, you don't see the position and momentum of every single molecule in the air. What you see are some macroscopic, coarse-grained features. You see the density, the temperature, the velocity at different points in the room. And so Boltzmann points out that there are many, many ways to arrange the molecules to give you exactly the same macroscopic features. So he says we should define a macro state to be the set of all microscopic configurations of stuff that look the same to us macroscopically. And then you can argue about what it means to look the same, but it ends up to not matter what it means. We all know what it means, and that's good enough. So then what happens is you have the space of all the possible states for the air molecules, and you divide them up into equivalence classes according to, do they look macroscopically identical? And then Boltzmann's equation here is just saying that the entropy is simply the logarithm of the number of microstates in whatever macro state you find yourself in. So in that definition, with that definition, it's perfectly obvious why entropy tends to increase. Because if you start with a low entropy state and you just wander off randomly into phase space, there are many more high entropy states than low entropy ones. So it is just highly probable that you will have an increasing entropy as a function of time. This bothers people for many reasons. For one thing, it's not absolutely certain that you will have entropy increasing. You could imagine entropy going down. There could be fluctuations, and that bugged people, and Boltzmann had to convince them that was okay. The other thing, of course, is that you hopefully detected the hidden assumption in Boltzmann's argument. Why does entropy tend to increase? Because if you start with low entropy, there's more ways to be high entropy. But you're allowed to ask, why did we ever start with low entropy? And Boltzmann did not explain that, and we have not explained that, and this is not explained right now. And that still bothers people. There's been 150 years of people arguing about proving the second law based on kinetic theory or statistical mechanics, and the reason why it's hard is because it's impossible. You can't do it just given the formalism of statistical mechanics. And this is pointed out immediately. It was not a late discovery. Loschmidt, who is Boltzmann's mentor, points out Sure, if you start in a low entropy state, you will probably go to higher entropy, but because the underlying laws of physics are reversible, for every trajectory that goes from low to high, there's another trajectory that goes from high to low. The number of trajectories along which entropy is increasing equals the number of trajectories along which entropy is decreasing. So you haven't proven anything about why entropy increases unless you assume that you start with low entropy. So that's essentially what we have to do. That is the state of the art. What Boltzmann essentially does is prove why the entropy of the universe will be higher tomorrow than it is today. What he does not prove is why it was lower yesterday than it is today. So here's a plot that you don't usually see. This is a plot of entropy in a box of gas, except instead of putting a low entropy boundary condition in the past, I put a low entropy boundary condition in the middle. And you evolve it both directions of time. And guess what? The entropy goes up toward the future, and it also goes up toward the past. Because the underlying laws of physics are completely symmetric. They don't know any difference between the past and the future. So if this is today, Boltzmann explains to you why you should expect the entropy to have been higher to go up in the future, but he also predicts that it should have been higher in the past, and nobody believes that is true. So you need to fix this. Boltzmann's formalism all by itself gets the wrong answer for the past. If you take this seriously, what it's saying is that all of your memories, all of the idea that you grew up and slowly evolved and so forth, these are not true. These sort of randomly fluctuated as a thermal fluctuation into existence in this room right now. And that's not something anybody wants to believe. So why was the entropy lower in the past? This is a challenge. And it's a cosmological challenge. If you want to know the answer, why was the entropy of the universe lower yesterday than it is today? The answer is because it was even lower the day before yesterday. Why was it even lower the day before yesterday? Because it was even lower the day before that. And this logic goes back 13.8 billion years until the Big Bang. So this is fundamentally a challenge for we cosmologists. So Boltzmann knew about this challenge and he tried to address it. So, since he was the first one to catch on to the fact that the second law is a statistical law rather than an absolute law, he said, if you wait long enough, there will be fluctuations downward in entropy. Boltzmann was thinking in the 1890s in this case, so he didn't know about the Big Bang, general relativity, or something like that. He lived in an absolute Newtonian space-time that was eternal, and he imagined, if you just scatter the universe full of particles with some temperature and let them go, even a high entropy configuration will sometimes fluctuate into lower entropy. So if you have a gas in this room, it's in a pretty high entropy configuration right now. It's smoothly distributed throughout the room, almost in thermal equilibrium. But if you wait, there's sort of a standard undergraduate exercise to do. If you wait just through the random motions of the molecules, you will eventually find a point where all of the air is on one side of the room, or in one corner of the room, or what have you. So here's a different plot. This is entropy as a function of time, but just homing in on no special boundary conditions at all. It's usually in equilibrium, but it fluctuates. There are small fluctuations downward. Equilibrium is the maximum here, so you can only go down. And eventually, if you wait, you get a relatively large fluctuation into low entropy configuration, and then it will bounce back. So Boltzmann said, well, what if we live here at this point marked X? What if we live in a universe that just fluctuates and eventually goes very low and bounces back up? And that's where we happen to find ourselves. So what Boltzmann invented in 1895 is two important concepts to cosmology today: the multiverse and the entropic principle. What he says was, remember, Newtonian space and time, infinitely big, infinitely old. He says usually the universe will be in thermal equilibrium. What that means is that usually, in his mind, that there's essentially a uniform collection of gas and dust and what have you. But occasionally there will be fluctuations. So there will be small regions in space where you fluctuate to a lower entropy state. Boltzmann also understood that we can't live in equilibrium. That life, literally life itself, relies on the fact that we are departing from equilibrium. We are chewing our food, we're processing information in our brain and so forth. All of these are highly out of equilibrium processes. So these regions of the universe, even though they're vastly dominant, are what he called dead. There's no life there. It's only in the regions where you get a large fluctuation away from equilibrium that life can possibly exist. So this is the multiverse. There's many different regions in space and in time where you have a temporary deviation from maximum entropy, and that is where you will find intelligent observers. Then he uses the anthropic principle to say, even though most of the universe is in equilibrium, observers only find themselves in the low entropy bits. Maybe that's why we live there. So it's a very familiar kind of argument to modern cosmologists. It's also completely wrong. I'm not advocating this point of view. It was a good try. It played by the rules. He didn't, almost every attempt to explain the arrow of time sneaks in some assumption that is intrinsically asymmetric to the past versus the future. This one does not. It just doesn't work. And here's why it doesn't work. As far as I know, this was figured out by Arthur Eddington in 1931. So what Boltzmann should have known, because he was Boltzmann, is that it's not only the case that there are fluctuations, but we can calculate the probability of a fluctuation. The probability downward, you see there's a lot more small fluctuations than big ones, which is not surprising. In fact, the probability of a fluctuation downward in entropy by delta S is exponential. It's e to the minus delta S. So what that means is that you tell me what your favorite anthropic criterion is. When do you count a universe as hospitable to life? So you have an infinite number of arguments about that. You need, a whole ecosystem, a whole galaxy, or whatever you need. I don't care. You tell me what you need. What Boltzmann's scenario predicts is that you will get that, and then the rest of the universe will be as high entropy as it can possibly be. So it's difficult to really absorb the lesson of this, again, because we are embedded in this arrow of time. We're embedded in a way of looking at the universe, and this is a very different way. What Boltzmann is saying is the following, or what Eddington is saying is the following. Take this room that we're in right now, including you and me, take the macro state of this room. All of us here, and we have brains, we have impressions in our brains of the outside world. We think that there's something outside called Paris and something further away called California and so forth. So take all the condition in this world, in this room, as fixed. Boltzmann says that if you wait long enough, rooms like this, with you and me in exactly our macro condition, will fluctuate into existence over and over and over again an infinite number of times. But the overwhelming majority of times that we fluctuate into existence, if we were to walk outside, it would be thermal equilibrium. There would be no city called Paris out there. There would be no state called California very far away. Because given the difficulty of fluctuating the idea of Paris into our brains, it is much more difficult to fluctuate the actual city of Paris into existence, just by random motions of the molecules in the universe. So if you were in this scenario, you would have no reason to believe anything that we traditionally believe about the universe. And the reductio ad absurdum of this argument was given by Albrecht and Sorbo in 2004. They said, if what you are asking for is what is a typical observer in the universe, it won't be you or me. It'll be just a single observer who fluctuates into existence out of the random chaos. And in fact, you don't even need that observer to have a body. It just needs to be a single collection of molecules that is complex enough to form a brain that can have a thought, that can look around and go, thermal equilibrium, and then it will die. And the overwhelming majority of intelligent observers in this scenario are of that form, and these are called Boltzmann brains. This is a mislabeled picture. This is not Boltzmann's brain. Boltzmann's brain is underneath the tombstone with the equation on it. This is a Boltzmann brain, and that's what a typical observer would be. And so there's an argument that is sort of casual and not exactly rigorous that says a typical observer is a Boltzmann brain, we are not a Boltzmann brain, therefore this scenario cannot be right. That's not really the right argument, and for the more philosophically inclined, there's a better argument, which is that forget about the Boltzmann brains. You're not a Boltzmann brain, you know that, and it's okay to just say, I don't care that there are many Boltzmann brains because I'm not one of them. That's not really the problem. The problem is the Boltzmann room that we're in. The problem is that what I already told you is that lecture halls like this will fluctuate into existence an infinite number of times. And the overwhelming majority of those fluctuations, we will have no connection to the outside world, no reliable correlation with the ideas in our head and the external reality. So even if this is the correct theory of the world, you would have no reason to believe this was the correct theory of the world, because your theory predicts that all of your impressions about the laws of physics and the rules of logic and the external conditions have randomly fluctuated into your brain. So this theory cannot simultaneously be true and justified. The technical term is it is cognitively unstable. You cannot believe it and have a good reason for believing it at the same time. That doesn't mean it couldn't be true. It might be true. It might be true that we're all, living in a computer simulation, that we're brains in vats, that we're taunted by evil demons. Many things could be true. This is an ancient French tradition of thinking of these things. But there's no way to live, right? You can't actually make progress that way. The alternative is to come up with a better cosmological scenario in which this is not true. How do you do that? Well, again, the state of the art is you make an assumption. This assumption goes under the quite non-glorious name of the past hypothesis. And the past hypothesis is simply the statement that our universe started in a low entropy state. That's all it is. It's an extra assumption in addition to the dynamical rules of Boltzmann's statistical mechanics. And you might think to yourself, well, wait a minute, I don't need to assume the early universe was low entropy. I know the early universe was low entropy because I've observed the early universe. Here's a picture of the early universe. Cosmic microwave background, and it is pretty darn smooth, right? Fluctuations of 1 part in 10 to the 5. And you need to go, there's a little back and forth in your head because the air in this room is pretty smooth, and the air in this room is high entropy, it's in thermal equilibrium. The early universe is pretty smooth, but it is very, very low entropy. What's going on there is that the conditions in the early universe are very different. The densities are much higher, the gravitational pull of the matter is enormously more influential in the early universe than it is through the air in this room. If you look at the phase space of the early universe, the overwhelming majority of possible configurations are wildly inhomogeneous. There should be black holes and white holes and empty patches and so forth. The fact that the early universe was so homogeneous is, in fact, a statement that it has low entropy. It's in a very rare, unusual, unlikely, orderly state. So you say, okay, that's not a hypothesis at all, that's data. But there you're wrong. I mean, it's true, the early universe did have low entropy, but this data is not why we know that. The problem is, this data is not the early universe. This is not a picture of the early universe. What is this a picture of? It's a picture of the microwave background radiation field in the vicinity of our telescope, here near the Earth, 13.8 billion years after the Big Bang. We use the radiation field nearby here to infer something about the early universe based on our theories. Part of that theory is that the early universe had low entropy, so it's cheating. If all you have is this data, and you say, what are the possible configurations of stuff in the early universe that would give radiation in my telescope that was very smooth, once again, the overwhelming majority of them are wildly inhomogeneous, but with very subtle, sneaky correlations so that those inhomogeneities cancel out by the time the radiation gets to us. So the actual temperature of the early universe could be very different from point to point, but the Doppler effects could be exactly canceling it out, or the gravitational redshift, or so forth. The data that say that the radiation field is isotropic is not nearly strong enough to tell us that the early universe was actually smooth. It's just that the combination of the data and the assumption that the early universe had low entropy is enough to tell us that the early universe is smooth. So we actually do need a hypothesis. It's an assumption. It's not part of physics. We would like to explain it. Now those are a bunch of words. I can actually make it a little bit more quantitative for those people who like equations rather than words. It has been done. So general relativity is the theory that we use to describe the universe on large scales. We don't understand all the details about quantum gravity and so forth, but cosmological perturbation theory, or just the expansion history of the universe, is well defined by general relativity. And general relativity is a classical theory. It has a Hamiltonian description. You can write down phase space with coordinates and momentum. And then you have Liouville's theorem. You have a statement that there is a measure on phase space given to you by Liouville. And you can ask the relative measure of certain configurations versus other configurations. Now in cosmology, what we care about is not the configuration, the states, the point in phase space. What we care about is the history of the universe. If we want to say that a certain trajectory through phase space is likely or unlikely, generic and robust, or delicately finely tuned. So you can do that. There was a very nice paper in 1986 by Gibbons, Hawking, and Stewart, where they took, this is the phase space of cosmological histories, and there's a constraint, the Hamiltonian constraint in general relativity, and then you look at all the trajectories that are compatible with that constraint, and you can find a measure. This is just inspirational, I'm not going to explain it, but it's a measure on the space of trajectories. And then you can ask yourself, given the data of the universe today, or given the data at recombination, what is a typical likely measure, likely trajectory history of the universe? And when you do this, you get some surprises. So you may be familiar with the flatness problem. The flatness problem is the statement that there's a spatial curvature in the universe, but the spatial curvature dilutes away more slowly than matter or radiation. So if you had any amount of spatial curvature, if you didn't have inflation, and you had a small spatial curvature in the early universe, it would dominate today. Why doesn't it? Why is the universe so flat? But that problem assumes that in the early universe, you were equally likely to have any value of spatial curvature, maybe between plus or minus 1 in some Planck units or something like that. There's an implicit flat measure on the space of possible universes that makes the flatness problem seem like a problem. If it were the case that a randomly chosen universe was always flat, then there would be no flatness problem. So you can take the Gibbons-Hawking-Stewart measure and apply it to the early universe and ask, what is the measure? You don't need to guess. There's an actual measure. And the actual measure looks like this. It goes as the curvature to the minus 5/2 power, which is non-normalizable. It's infinitely big. But if you regularize it, the point is that there is more measure at 0 than at all other points combined. So in other words, it is true. If you take a Robertson-Walker universe and pick it out of a hat, it will be flat, exactly flat, with probability 1. The whole flatness problem that you've been told has been a fake for all these years. And I'm the only one to tell it to you, but I'll keep telling it to you. It's not a real problem, the flatness problem. So learning this, you might say, well, that's encouraging. Maybe the whole fine-tuning problem of the early universe, maybe the horizon problem is also a fake. Sadly, that is not true. The horizon problem is totally correct. So one way of saying it is the following. Imagine that, just for illustration purposes, imagine that you really do believe in your soul that the CMB, the conventional interpretation of the CMB is completely correct. That there were small fluctuations in density, 1 part in 10 to the 5. So here's today, here's the CMB, here's the past. Imagine that delta rho over rho really was 10 to the minus 5 at recombination. But that's all you're allowed to imagine. We're doing a thought experiment. Let's not assume any more than that. So in cosmological perturbation theory, there are growing modes and decaying modes. And usually, given any initial condition, we just follow the growing modes because they grow with time. But a priori, without any extra assumptions, you could have decaying modes as well. And so in our thought experiment at the CMB, there is a measure on the space of trajectories that give weight to both the growing modes and the decaying modes. And generically, as you go toward the past, that decaying mode implies that the universe before the CMB was more and more inhomogeneous. And in fact, you can ask, what is the fraction of trajectories that are not only smooth at the CMB, but also smooth in the earlier universe? And that fraction is 1 part in, well, that fraction is 10 to the minus 10 to the 17. It doesn't matter what the number is. It's preposterously small. So that is exactly the same argument I gave you about the entropies if I didn't use the word entropy. The point is that some people say, well, we don't know what the entropy is when we talk about gravity and so forth. It doesn't matter. The point is the actual trajectory that we believe the actual universe followed is extraordinarily small in the space of all possible trajectories. That's what cosmologists need to explain. Once you do explain it, you get a lot that follows from that. For example, I said to you that it's the thermodynamic arrow of time, the past hypothesis, that lets you remember the past but not the future, right? Well, why is that true? So here is a memory. This memory is an egg that is broken on the sidewalk. And why do I call this a memory? Because from this, we can deduce something reliable about the past. If you ask what is the future of this egg going to hold, you don't know. There's many different possibilities. It could wash away, a dog could come along and eat it, somebody could clean it up. There's many different possible futures. But if you ask what was the past of this egg recently, with high reliability, there was an unbroken egg that somebody dropped, right? Now, why do you have a better idea about the last day in the life of this egg versus the next day in the life of this egg? Where is that asymmetry coming from? If you just do mechanics, if you just study the micro states of all the possible atoms in that egg, there's some possible futures, there's some possible past, and there's an equal number of them. The reason why you think you know more about the past than the future is because you're also assuming the past hypothesis, that there was a low entropy condition in the past, that that egg did not randomly fluctuate onto the sidewalk, that it came from an unbroken egg, and that is what allows you to draw the correct reconstruction of the history of the egg in that particular way. And this is true not only for eggs, this is true for history books, for photographs, for historical documents, for computer records, for memories in your brain. They are states of the current universe that you can reliably correlate with events in the past because there was a low entropy condition at early time. So, want to distinguish what we do know and what we don't know. What we know is that I keep forgetting that there's a typo on this slide. We do know that entropy will increase toward the future because that's what Boltzmann said. We actually don't know why it was lower in the past. We know that the entropy was lower in the past. What we're trying to figure out is why it was lower in the past. So the word why should not be there. And then how we want to work out the details of how it all explains the different manifestations of the arrow of time. So let me, just because it's fun, and I like thinking about it, let me give you one little aside that is helpful in thinking about this, the distinction between entropy and complexity. So here's the history of the universe in 5 chapters. In early times, the universe was hot, dense, and smooth. 1 second after the Big Bang, this was the beginning, the onset of nucleosynthesis. It was just white-hot universe everywhere. As time goes on, it cools, it gets dilute, and gravity takes over and starts pulling things together. So you get the CMB, and you get our universe today, with stars and gas and galaxies. Most potted lectures on cosmology stop there, but there's no reason not to extend into the future. You should treat the future just like you treat the past. So what will happen? Well, all the stars will burn out, they will use up their nuclear fuel, and the stars will basically fall into the black holes. And so about 10 to 15 years in the future, the last star will cease shining, we're living in a dark universe. Those stars and the planets will eventually fall into black holes, but the black holes will eventually radiate. Black holes do not last forever. Hawking says that black holes radiate to space. So about 10 to the 100 years in the future, the last black hole will completely radiate away. This is assuming that the universe is driven by dark energy, which will not go away, will not recollapse or anything like that. If that's true, then in the future, the universe will be absolutely dark, absolutely empty, cold, dark, desolate space. Now you notice that entropy, you don't notice, but I will tell you that entropy is increasing from left to right here. If you actually plug in the numbers, this is a low entropy state, this is a high entropy state. It's been increasing all the way. But the complexity or simplicity in the universe does something else. The early universe is a very simple place. Hot, dense, and smooth. Rapidly expanding. That's a full, you can add a little bit about the ingredients and so forth, but that's basically a complete description of the early universe. The late universe is also a very simple place. It's empty. That's basically the whole description of the late universe. Value of a vacuum energy or whatever you mean. It's in between that the universe is complex. That's when you have galaxies and stars and seminars and things like that. So the entropy just goes up, but the complexity goes up and then goes down. This is not an unusual or unique feature of the universe. This is absolutely generic. It's true as a cup of coffee. This is a very simple state. This is another very simple state. The milk is on top, coffee's on the bottom, everything is mixed together. Entropy just goes up from left to right, but it's in the middle where you have all the tendrils and all the mixture of the coffee in interesting ways that things look potentially complex. So again, entropy goes up, the complexity goes up, and then goes down again. So in the US, we have to deal with creationists. who believe that the evolution of life is incompatible with the second law of thermodynamics. They say, the second law just says that everything winds down and becomes boring, and how could life come into existence? The point is, the second law doesn't say that. It's not only that the evolution of life is compatible with the second law, the evolution of life happens because entropy is increasing. That's what allows complexity to form. So this is a wonderful little picture drawn by a famous artist named Roger Penrose. And what it's depicting is life here on Earth. You know, we get radiation from the sun, and sometimes you informally say that the sun's light gives us energy. But that's not the right way to think about it. It is true that there's energy in the light from the sun, but we give back exactly the same amount of energy back to the universe. Recently, we've been giving back a little bit less. And that gives us global warming. But other than that, to a very good approximation, we radiate the same amount of energy as we get from the sun. The difference is, for every one photon we get from the sun, we radiate 20 photons back to the universe. We get visible light from the sun. We radiate 20 infrared photons with 1/20th the energy each. So 20 times as much entropy in the energy that we give back to the universe. So we've been increasing the entropy of that energy by photosynthesizing, chewing our cud, thinking, eating, getting through our lives. So it is not just that we human beings are compatible with the second law. We are increasing the entropy of the universe in a dramatic way. In fact, this is, in a very, very reasonable, plausible scenario, this is why life exists in the first place. If you go back to the atmosphere of the prebiotic Earth, it was dominated by carbon dioxide and water. So there's a lot of, and hydrogen, I should say, sorry. So there's a lot of carbon dioxide in the air, and it was a low entropy state. It would have been much higher entropy for that carbon dioxide to turn into methane and water. So carbon dioxide plus hydrogen wants to be methane plus water. This is the free energy. You release a lot of free energy by getting there, but there's no simple reaction that takes you there. To go from carbon dioxide to methane requires going upward in free energy. There's a potential barrier to getting there. What that means is there's no single simple reaction that does it. You need a complex sequence of reactions. You need a barrier that protons can go through in one direction but not the other. You need a complex chain of metabolism that eventually forms the pathways that give rise to life, according to, again, a very plausible scenario. So that's what we do. That's why we're here. You and me, we exist to help the universe increase its entropy in our own minor way. And the complexity of us is an outgrowth of that. So to sort of quantify this idea, some of us did a little computer simulation of cream mixing into coffee. This is the simplest thing you could think to do. So here's cream and coffee mixing together under two Hamiltonians, one of which they totally don't interact with each other. They're smoothly passed through. The other one, the cream molecules and the coffee molecules bump in and catch on and interact with each other in different ways. And you can plot the entropy, which just goes up, and the complexity, which doesn't do that much in the non-interacting model. In the interacting model, the complexity goes up and then goes back down again, as predicted. This is not the most convincing graph in the world. I would grant you that. But I think that astronomers give you a bunch of slack when you show graphs like this. Like, oh yeah, I can see at least 5 different lines of different things. So this is a general principle. It has nothing to do with the cosmology that I want to talk about, but it helps connect our sort of informal notions of complexity and organization to the fact that the entropy of the universe is simply monotonically increasing. Okay, so back to why we're here, which is the cosmology. We want to come up with a theory of the universe that does not simply assume a low entropy past, but explains the low entropy past. That tells us why it is not surprising that our Big Bang conditions were so low entropy. So remember what the history of the universe is. Here is again the Lambda-CDM model. And an important ingredient here is the cosmological constant, because that's what tells us that the universe will not recollapse. And note that even before you do any thinking about it, this cosmological scenario is already a little surprising or bizarre. We live 10 to 10 years after the Big Bang, about 10 to 10 years, and that seems like a long time. But you're saying here that the future history of the universe is infinity years. We live really, really close to the beginning of the universe by any natural measure. So why is that? Why are we so lucky to live close to early universe? That's a good question. But let's concentrate on the future a little bit. So the fact that we have vacuum energy, the fact that there's a cosmological constant, of course, if it's quintessence or something like that, all bets are off. So let's just assume for this lecture that it is truly vacuum energy. So here's the universe, here's you, here's a friend of yours that went on a little trip far away. And in a universe dominated by vacuum energy, the universe expands forever at a fixed rate. So these are arrows, it's hard to see them, but the universe is expanding in all directions. And a fixed amount of vacuum energy means that the Hubble parameter asymptotes to a fixed value. So the time scale over which the universe doubles in size is a constant. It exponentiates over time. What that means is that there will be a point past which signals can no longer reach you. So you will be surrounded by a horizon in a universe dominated by vacuum energy. If you think about the apparent velocity of distant galaxies, it goes up Hubble's law. The further away you are, the faster the apparent velocity is. But Hubble's law generally doesn't mean that things can't get to you because the Hubble constant itself is decreasing in a matter and radiation-dominated universe. But in a universe dominated with vacuum energy, the Hubble constant is a constant. So if someone else is so far away from you that their apparent recession velocity is greater than the speed of light, then they are outside your horizon. They cannot possibly either get to you or send any signal that you will ever be able to get to. So this person and this person can run together as fast as they can, but the space-time in between them is moving apart so fast they will never be able to link up. So there's a horizon around you. Back in the 1970s, Stephen Hawking studied black holes and showed that the horizon around a black hole is not as black as you thought. It gives off radiation when you take into account quantum field theory in that horizon. And a couple of years later, Hawking and Gibbons showed exactly the same was true for cosmological horizons, except that we're now on the inside rather than outside. So in this universe, the cosmological horizon has a temperature. It gives off radiation that gets to us. The temperature is very, very tiny. For realistic units, for realistic numbers, the temperature of our vacuum state will be about 10 to the minus 30 Kelvin, as compared to 3 Kelvin that the CMB is today. So it's much, much colder than our current universe. And it's also associated with an entropy, which is really, really big, 10 to the 120. The entropy within our horizon size today is about 10 to the 103. It's dominated by supermassive black holes at the centers of galaxies. In the early universe, it was something like 10 to the 88, the total number of particles of radiation. So this is as large as the entropy could be. 10 to the 120 is much, much larger than 10 to the 103. They sound similar. But remember that the entropy is the logarithm of the number of states that macroscopically look this way. So the number of states that look this way is enormously larger than the number of states that look like our current universe. But so what is that future going to be like? Well, we said it's empty. There's nothing happening in that empty space, except for these little fluctuations, except for this temperature, which causes thermal fluctuation. And what that means is that Boltzmann was right. That scenario that I told you couldn't possibly be right, where you live in an eternal universe with thermal fluctuations fluctuating in the brains and so forth, we now call lambda CDM. That is what our future holds. There's vacuum fluctuations, thermal fluctuations with a temperature. If you wait long enough, you will fluctuate. You will have these photons come together. Usually the photons are very, very long wavelength and soft, but if you wait long enough, a couple of photons on the tail of the thermal distribution will bump into each other and make an E plus E minus pair. If you wait longer than that, you'll make a whole bunch of particles that will form into a virus. If you wait longer than that, you'll make a whole bunch of particles that will form into a brain, or a person, or a planet, or a galaxy, or the whole universe. You just have to wait long enough. And you have infinity years to wait. So even though the rates are very small, all of those things will happen. Because the entropy is large but finite, within any one horizon volume, there is a finite dimensional Hilbert space that gives you the quantum mechanical description of what's going on. There's only a finite number of things that can happen in a horizon volume. And there are infinity years over which they can happen. So everything that can happen will happen an infinite number of times. And in fact, over the course of 10 to the 120 years, you will cycle through everything that could possibly happen, and then it will happen over and over and over again. So this is bad. This means that that thing that was wrong with our lecture hall fluctuating randomly into existence over and over again, with no correlations between our brain states and the outside world, is the theory that all cosmologists believe is most likely to be right. But it can't be right, because it has this cognitive instability problem. We need to do better. Lambda CDM cannot be the whole story. So how to escape that story? How to do better than that? Well, the simplest way to do better than that is to let the vacuum energy go away. To change the value of the vacuum energy. You could do that with quintessence, but you could also do that if you just live in a false vacuum. So if there's some potential energy in some field, and we live here with a tiny amount of our current day vacuum energy, and there's some other vacuum state with a lower energy, then in the future we will undergo quantum tunneling from there to there, and the cosmological constant will go away, and so will the Boltzmann brains. So you may look in your favorite theory of grand unification or supersymmetry or string theory, are there appropriate fields that might do this? The good news is you don't have to look very far. There's the Higgs boson. We just discovered it last year. I wrote a book about it that you can buy right now on your iPhone on Amazon. And that Higgs field, we've now measured its parameters. It has basically two parameters. Its expectation value, which we've known for a long time, and its mass, which we just learned last year. It's 125.5 GeV. So given those parameters, you can use the renormalization group to calculate the whole potential from 0 to however big you want to go. Interestingly, for the parameters that we have measured, it seems that the potential doesn't do the conventional thing that you would guess and apply to the fourth theory, but the renormalized potential turns over. It seems as if at large field values, near the gut scale or the Planck scale, there is another vacuum that the Higgs field could be in. And it might be lower than ours. We might actually live in a false vacuum. This other vacuum could be positive, negative, or zero vacuum energy. We don't know. Our measurements are not precise enough. It is really weird and provocative that not only does this vacuum exist, but it's really apparently pretty close in vacuum energy to our current vacuum. There's no a priori reason that should be true. This is another weird cosmic coincidence to add to your list of weird things about the universe. Why is the other vacuum of the Higgs field similar in vacuum energy to ours, even though they're separated by many, many, many GeV in field value? So we could, in the future, go transition from here to there. So you want to know, do we do it fast enough to avoid the Boltzmann brains? The bad news is that to avoid the Boltzmann brains, this transition from one vacuum state to another has to be very fast. The time scale has to be about 10 billion years. So that doesn't mean like it will happen tomorrow, but it does mean it could plausibly happen in the next 10 or 20 billion years. So it's not a matter of rebalancing your retirement funds or anything like that, but all of the history of cosmology that I told you about the stars burning out and black holes and so forth, will all be nonsense if this is true, because the vacuum energy will go away. So does it go away fast enough? Well, I just wrote a paper with one of my students looking at that. And here is the parameter space that is relevant. This is the mass of the Higgs boson in GeV. Here we are at 125 and a bit. Here's the mass of the top quark, which is actually the most important for this. So if the top quark is light enough, then you're perfectly stable. Then in fact, the other vacuum state is higher energy than ours. If it's heavy, then you rapidly decay, and you're safe from the Boltzmann brains. If it's in between, then you're metastable, so there's some long lifetime. The lifetime is usually very, very long. So here's the current favorite value, if you believe what you read in the particle data group. We're in the metastability band. So we won't decay quickly, but we will someday decay. And usually, the other people who've written about this have had the psychological attitude that it would be bad if our vacuum decayed, because that's kind of scary. So they always ask, is it possible that we live in a stable regime? But we were asking, no, we want to avoid the Boltzmann brains. Is it possible that we decay fast enough to get rid of the Boltzmann brains? So these error bars here in the middle are, again, what you read in the conventional particle data group, and we're about 5 sigma away from this red line, which is where we want to be. In order to get rid of the Boltzmann brains, we need to live on this red line. However, it turns out there's a little bit of controversy in the particle physics literature about the mass of the top quark. The mass of the top quark is hard to measure because it's not a stable particle. They're hard to produce. So someone reanalyzed, actually it's the CMS collaboration, reanalyzed their data using a slightly different definition of the mass of the top quark, one that fits better with the potential of the Higgs field that we were talking about, and they got these error bars, the bigger ones. And this is 1 sigma and 2 sigma. So it is at least conceivable that the real mass of the top quark is something like 178 GeV, in which case our universe is only going to last another 10 billion years or so before the Higgs vacuum decays and total disaster strikes. And at least we'll be safe from the menace of the Boltzmann ring. All right, that was a little aside. So that could be the answer. What other answers are available? Inflation is not the answer. So I'm sorry, I should say the Higgs story could be the answer to getting rid of the Boltzmann rings. It is not the answer to why the early universe had low entropy. Inflation purports to be the answer to why the early universe had low entropy, but it failed. It does not actually answer that. So here's the story of inflation. It's a very similar story to what we just said. There's some field that has potential energy. There's a false vacuum and a true vacuum. There may or may not be a barrier in between them, whether you're doing slow roll inflation or false vacuum inflation. But the point is, if you have a little patch of space where the energy density is dominated by the potential of the inflaton in its false vacuum, then it expands very, very rapidly. It smooths out all the inhomogeneities. It makes the universe flat. The usual story of inflationary cosmology. And all that is true. So in comparison to this is the Big Bang model, where we have a relatively big early universe. So as a matter of fact, if you take our horizon today, in the conventional non-inflationary Big Bang model, if you evolve it back to the Planck time, you hit the Planck time when our co-moving volume is about 1 centimeter across. So that seems small to fit 10 to the 88 particles and 100 billion galaxies in there, but it's actually huge compared to particle physics length scales, right? A centimeter is bigger than any known particle physics length scale. So that's a question, why was the universe so smooth over a 1 centimeter length scale? With inflation, you can start the universe in a much tinier patch. You can be as small as you want. You can be the Planck scale or even smaller than that. And from that, you can inflate into the whole universe, and that's one of the benefits of inflation. The question is, does this scenario explain why the early universe had low entropy? The usual story you are told is that as long as you start in that false vacuum, you explain everything that we need to explain about the early universe. Why it's smooth, why it's flat, where the perturbations came from. The problem is you don't actually explain the low entropy. You do account for the low entropy in the sense that if that happens, you will in fact get the kind of universe we see. But the point is, you started in this false vacuum state, and you can ask what the entropy was of that. And the answer is something like 10 to the 12, or 10 to some number of order 1 or 10 or something like that, which is enormously smaller than the entropy of the conventional early universe in the Big Bang model. So in other words, what inflation is doing is saying, the reason why the early universe had such a low entropy is because it started in this state with even lower entropy. Well, okay, maybe that happened, but it's not an explanation for why the early universe had a low entropy. You cheated.